Hey Keith, we got lecture 5 today. This one's all going to be about hardware. You remember we had a good lecture on this last year, but it was a little heavy on the theory. I thought what we might do is include the lecture from last year, and then you can add some stuff that's more practical because that's pretty fun.
Yep. Towards the end, we're addressing the students' requests for a little bit more. How could I build this myself? And we've heard you, so you'll get there. But of course, Kim, as always, we have to know the theory before we can know the practical outcomes.
Right. So let's just queue up what we're going to do, and then we're going to cut to the other lecture that we already have recorded. So first of all, here we're going to talk about piezoelectric crystals, resonant frequency, backing, matching layers, transducer spec sheets, and then we're going to cut to the other lecture that you're going to give. Okay.
Sounds good. Let's jump in.
All right, so piezoelectric crystals. PZT, lead zirconate titanium, is the most common material. Other crystals are used for transducer creation, but PZT is the most common. The basic idea is that the crystals are oriented randomly, and then once they're heated beyond the Curie temperature, which is 365 degrees C for PZT, then that frees those microscopic crystals and they allows them to move. So you put a voltage across them, and then you cool the material while that voltage is across them. So the voltage creates a realignment of those crystals, and then if you cool it, then they are kind of frozen in place. Now, once you have that PZT in that sort of configuration, and by the way, this is called poling. Once they're in that configuration, now they're going to undergo the piezo effect. So there's two parts to that. First, there's the direct effect. The idea here is that if you have a pressure wave, then you're creating pressure on the crystal. Then those individual crystals in there are going to realign. And when they realign, there's going to be a voltage difference across the two surfaces. So if you put an electrode on the top, front, and the back, then you can measure that voltage. So that's the basic idea of what happens on the receive side of ultrasound. So you put it up against the tissue, and then the pressure wave that comes back from the tissue is going to create a pressure change. It's going to deform the crystal, and then you can create a voltage that can be picked up by the computer. So that's the direct effect. And then there's the reverse effect. Now here I've shown up against some material with some molecules. And the reverse effect is that if you put that voltage change across the two faces of the transducer, then you're going to create the crystals to realign. And that's going to cause a deformation change, which is then going to put a pressure wave into your tissue. So that's what is done on the transmit side of ultrasound. Of course, since we're not really going to talk about ultrasound imaging, we're not so concerned with the direct effect on the left, but the reverse effect is what we are interested in because we are very, very interested in the transmit side of ultrasound.
I think the direct effect for any bioengineering students in the course might also come up in bioelectronics too. So you can implant small piezos within the body. And if you can send that pressure onto those, they can generate a voltage that can wirelessly power little devices in the body. So that's pretty neat.
Yeah, that is pretty cute. Okay, so just as an aside, we talked about this effect in PZT, but it turns out bone actually has a similar effect. That the collagen will exhibit this polar orientation. And so when you undergo pressure waves, then it basically will set up little electrical currents in the bone. And that has been shown to stimulate resorption and growth.
Does this have anything to do with this? It's not planned, but you know when you say I can feel it in my bones, like is there any relation to this? Or when people feel the weather patterns and like humidity? Is it related?
That I don't know. But I think what this is related to is if you think about, when old people have osteoporosis and they're told to exercise. Well, the act of exercising is putting pressure on their bones, repeated pressure, and that repeated pressure is going to stimulate bone growth. And so that's the basic idea there.
Right. Super interesting.
Yeah, it is. It turns out the long bones all have this sort of effect, but the skull doesn't respond to load like the long bones do. So we don't really know why the skull has different thicknesses, because it doesn't respond to load. All right, but let's get back to the topic at hand. Let's talk about the PZT. And this is a table now of the density, speed of sound, and impedance. And what we see is the PZT has a very, very different impedance from soft tissue or fat. So what do you think this is going to do if you put up a transducer right up against the skin?
Is that a question for me, Kim?
Yes, it is.
I think you're going to get some reflection and some transmittance.
Yeah, a lot of reflection right there. So we'll talk a little bit about matching layers and how that will reduce the reflection. But first of all, let's talk a little bit about the transducer anatomy. So the transducer is shown in here in sort of the silver color. The electrodes are on the front and the back face there so that we can set up that voltage change. And then there's going to be a matching layer up front. And on the back, there's going to be a backing material. All right. So transducers will typically have a resonant frequency. This is determined by the thickness of that crystal. So here we have kind of a short crystal, not very thick, and there's going to be higher frequency than if we have a thicker crystal and it's lower frequency. So the basic idea is that you have a wave that's, if there's a wave that's going from the front into the back and then bounces off the back and comes to the front, if it goes through a full wavelength, then the initial wave and the reflected wave are then going to be coherent. They're going to be at the same phase, and you're going to get more power out through the transducer. So that's the basic idea, is if this is a half wavelength, then it sort of sets up resonance in the crystal and you get more power coming out. So it just says that the length of the transducer is typically a half wavelength times n, so where n are odd integers. So it can be 1 half wavelengths or 3 half wavelengths, or etc. And then just turning that around using the relationship that we're familiar with, using the speed of the piezoelectric crystal, then we can find what the resonant frequency is given the thickness or the length of the crystal. And so that's nice. We have a way to manipulate what the frequency is from the crystal. Next, we're going to talk about the backing layer. So it might be a solid backing layer. And then the effect that's going to have is to damp down the sound. It's almost like the tuning fork where you put your hand on it. It's going to damp it down. So it's going to make it sort of low Q. And that's as opposed to the air-backed system. This one is not going to damp down the crystal, which instead is going to ring and ring and ring and keep on ringing. And then that's going to have a very high Q. So that's air backing. This is the effect of backing. In the case where there's no backing or sort of air backed, you can see it rings a lot better than in the case where there's backing. So this is actually measured data. Now this is putting that all together so that you can see how you can start to manipulate the ultrasound that comes out of your transducer. You can change up the resonant frequency, and you can change up the backing material. Resonant frequency, of course, changes the frequency of the ultrasound, and the backing material changes the damping. So now we have 4 very different waveforms. So these are some of the knobs that we have to control when we're talking about ultrasound transducers.
And I think, correct me if I'm wrong, Kim, but the ring down time with the low Q or that damping is really important for imaging, right? But maybe not so important for ultrasound neuromodulation.
That's exactly right. For imaging, we usually want only a few cycles, maybe 3 cycles or so, because you want a really small pulse so that that gives you better resolution in your picture. For most of our neuromodulation applications, when we start talking about the essential tremor treatments, like we talked about last time, we want continuous wave for 20 seconds. So that's really, really long. We definitely want it to ring and ring and ring with an air-back transducer. For many of the neuromodulation applications where we're talking about it ringing for a millisecond, then that's a little bit less long. It's maybe you want something that's sort of lightly backed, but not backed like this one that's going to ring down in a couple of microseconds and not necessarily going to ring for 20 seconds. All right, and so I just wanted to remind you about the pulse frequency content. So if you have one that's air-backed and it rings for a long time, here I'm just showing you ringed, this one's just ringing for 1 millisecond, and it's relatively narrow band. And then that's compared to the case where it's really heavily damped and it only rings for a few seconds, a few cycles. So that's in just a few microseconds there. And then that's much broader band, even though they have the same center frequency. So the sinusoids have the same period, the same frequency. So their spectra are centered around the same point, but then they are the broadband is much broader frequency components. Okay, next I want to talk a little bit about the matching layer. The matching layer goes in the front, and the idea is that the transducer itself, the piezoelectric crystal, has a very, very different impedance than the soft tissue that it's up against. So the idea of the matching layer is to put in another layer with a different material, which is going to be in between the other two. And so in some sense, you can get better transmission through that matching layer if you've got that extra material in there. You'll have, instead of having like, almost 100% reflection, you'll end up having a smaller reflection through each of those interfaces. The other component of the matching layer is that usually the thickness is set to be a quarter wavelength. And this comes from transmission line theory, but we don't really have time to get into that. But if you do these two things, then it looks like the transducer has the same impedance as soft tissue. And so that really maximizes the transmission for one frequency. If you want it to have a really good transmission for several frequencies, then you might use multiple matching layers for multiple frequencies. And so coming up with exactly what the matching layer looks like is it's a perfectly reasonable homework question that people might see.
Sounds good.
All right, so let's look at the effect of the matching layer. So here we have the case where there's no matching in blue, and then with the matching layer in red, and you can see that there's a higher response. And then this is a case now where it's a quarter wavelength as compared to a half wavelength. And what we see is with the half wavelength, it's not optimal. It only went up to about 6 amps. And use the quarter wavelength has gone up much higher, now up to 10 amps. So much better transmission if you use the matching layer at a quarter wavelength. All right, and then lastly here, before we go onto our tour that Keith is going to give us, is the transducer spec sheets. And what do those look like? So this is an example of what it looks like. There's two plots superimposed. So in the black, we get the time signal. So this is showing you the pulse echo. So if you pulse it, and then what does the echo look like? And you can see that there's a number of cycles here. So you could actually count the period between 1 0 crossing and then one period later. What is the length of that period? And then that would give you, if you looked now at the blue, it gives you your frequency response. And so you could see the peak of that is the center frequency, and that should correspond to the period that you've calculated from the time signal. The other thing you can look at when you look at this is sort of the, not just the center frequency, but it can also look at sort of the bandwidth and the range of frequencies over which you can give reasonable signal. So this case, it's a transducer that has a low Q, it's damped down, it has kind of a broad frequency response. In some ways, this can be useful. So in this case, it's a 5 megahertz transducer. You can drive this transducer at 3 megahertz. You're not going to get quite as much signal, but you'll get reasonable signal. It's going to be a bit lower, but not too bad. And so it tells you how much lower that signal will be. All right, so we can compare this to the spec sheet for an air-back transducer with a high Q. And this one now, you can see that it rings quite a bit better. Looking at the pulse echo signal in black, and now looking at the frequency response in blue, what we see, again, we can see a center frequency around 5 megahertz, but we see that the bandwidth is much narrower. We look at half maximum. Well, this is in a dB scale, so the half maximum is going to be way up here, but it's much narrower in terms of the bandwidth. So this one now has about 15% bandwidth, and on the other case, it was about 50% bandwidth. So remember, Q is 1 over the bandwidth, so a smaller bandwidth is going to give you a much higher Q. Okay, so that's how you can look at these. This one also, because it has the lower bandwidth, it means you cannot drive it quite as well off frequency as you could the other one. One last point I wanted to make is about the efficiency of these transducers. So the efficiency is defined as the acoustic power, so sort of the output power, compared to the electrical power, the power that you're driving it at. And some of the airbag systems could have as high an efficiency as about 50%, so that's pretty good. Half the power you put in, you're going to get out on the transmit side. The other half is just going to be converted into heat. Heat isn't necessarily what we want. It's just going to heat up the transducer. It's not going to be very useful. So that's where cooling can come in and play a very important role. Especially if you have a continuous wave CW system, then you often really need that cooling. If you're going to be driving these transducers for, say, 20 seconds, then cooling can be essential.
Yeah, there's also a sort of interplay if sometimes people will attach heat sinks directly to their piezoelectrics, and then it's no longer an airbag system and you're getting less transmit, but it does help cool the elements much faster.
Okay, so Kim just got done telling you all about piezoelectric crystals. And while we're going to get into different ways to shape these crystals and build them for different focuses, right now we want to tell you how you can do like sort of a homebrew build to actually drive the crystal to get this expansion and contraction that we were looking at earlier. So what we're showing here is really like the bare bones, simplest way to do this. And this is a method and system that Kim and I use in both of our respective works. And the key principle here is that you have these sort of output functions. And as Kim mentioned, you're trying to oscillate a voltage across a crystal. And you're passing them into an amplifier to make them extremely large and to drive a lot of power. And then you're passing this oscillating signal onto your crystal, which is essentially ending up here in the plus or minus. So I'm going to break down each one of these parts and give you a flavor of how to use and build your own setup here. So let's start with the function generator. So these two in our diagram. So a function generator can look like a lot of different things, and there are a lot of companies that make many different ones. And we're going to look at an instance from Keysight, the 33210A. We're just going to point out a few components that you would find in any function generator so that when you approach one, you're ready to go. Kim, thoughts on that?
No, I'm all set, ready to go.
Ready to go. Okay, so the first thing, even before I jump into the individual buttons, the first thing to notice is that some of them have a keyboard sort of where you can punch in different values and make things easier. And a lot of them have a knob so you can just sort of rotate them across space. These are all common bits. Something that's not shown here is that in the back of this system, and sometimes it's over Wi-Fi or Bluetooth, is an interface so you can connect a PC, like we're showing in this diagram here. And there are ways to interface your PC to these function generators through MATLAB, Python, C++, you name it, and we can help you get there. And that allows you to automate sort of experimental control of your entire system. You can do it by hand, though, of course, too, and that's what I'm going to talk about now.
Yeah, we had a system for a while that, and I think we may still be using it, where it was monitoring something, and then given when we found out that what it was monitoring was really like kind of quiet and the animal was really quiet, then we would trigger the ultrasound to go on.
Oh, I'm glad you brought that up. Yeah, closed loop is probably the best instance of why would you want a PC to control this when you could do it by hand? And Kim, you just nailed it. You might be listening in with your same PC on what your animal or your subject is doing, and you want to close loop this thing. Mm-hmm. I'm glad you brought that up, Kim. So if you were still in the Stone Age and you're doing it by hand, though, maybe you're just trying to figure out your transducer, you'll start with these little buttons here. And you can see here that we have a sine wave, square wave, ramp. These buttons essentially are telling you what your wave that you're programming into this thing looks like. And again, your PC can say what your wave is. Typically, you'll use a sine wave because we're trying to smoothly oscillate the voltage across the crystal to get nice smooth expansion and contraction. You can also use a square wave because in the same way a sine wave works, you're going to get your positive and negative voltages. Although this can be dangerous at extremely high voltages because it can cause the crystal to expand or contract faster than it's really built to do.
So
just
you're talking about the fundamental frequency, right? So something like 500 kilohertz.
Yep, whatever your fundamental might be that your crystal will oscillate at. Kim, do you ever use the pulse or ramp function on a function generator?
No, I think for fundamental frequency, it's always just a sine wave.
Yeah, so you can probably skip over these, and you can even skip over noise. These are probably more for like radio frequency research. But another thing that we'll use commonly in ultrasound research is the arbitrary function button or waveform.
But you use it for the fundamental, or you use that for an envelope across the fundamental?
That's right. So we're not using it for the fundamental because those are so well sort of defined by just a sine wave. But you might use the arbitrary, and we'll get to this in a bit, to actually modulate or like give your waveform slow rise or slow decay by multiplying the two together.
Hey, but what if you wanted to change the fundamental on the fly? Like you wanted to have a frequency modulation. Would you use the arbitrary for that one?
So you can program in multiple arbitrary waveforms. And I guess you're asking, can you use different modulations in one sweep? Is that kind of
well, that wouldn't be an amplitude modulation, but how do you do a frequency modulation? So sweep through frequencies from, say, 500 kilohertz to 700 kilohertz.
Oh, okay. Yeah, that's a great question. We can actually even jump right into frequency sweep, and then we'll go back to the other bits. So Kim is asking, what if I want to do an experiment or a test where I start at 500 kilohertz and you go up to like a megahertz or something? Maybe a good example.
Yeah.
So these boards usually actually have a sweep function, and within the sweep function, it'll ask you, what's your starting frequency? What's your end frequency? And then what are your steps? So do you want to step by 10 kilohertz, by 100 kilohertz, and so on? And Kim, like what might you use this for? And then I'll say why I've used it in the past. What are some useful applications?
Well, one of the things I was thinking about was ways to minimize standing waves. Is if you are changing the frequency, kind of like every cycle, it's a different frequency, then they're not going to pile up on top of each other so easily.
Yeah, that's a great use. And you can probably measure that with a hydrophone setup, which I think we would have taught the students at this point. And another thing that I used to do a lot of, I don't know that Kim's ever done this. Kim, you can tell me, is something called a parametric frequency sweep. So I'll just start at the top here, but this is essentially where you step through all your frequencies and you're looking for some sort of outcome. In Kim's case, it might be, is there a standing wave? In my case, it was always, what is the pressure, excuse me, at the tip of this little fiber here? So I'll just walk you through what I was doing. I actually put a little single element piezoelectric crystal sandwiched between two metal tubes, and I was casting a voltage, like our sine wave and our fundamental frequency, across these tubes. So this essentially created the voltage, and I would get an ultrasonic wave that would propagate through this entire structure. So when I bought this piezo, there was an optimal frequency for just that element. So that deals with how wide is the element, what's the voltage, and so on. But once you start adding all of these other components and you're dealing with waves that are propagating across different acoustic impedances and reflections are coming back and things like that, then your optimal frequency may have very little to do with the piezo alone, but rather the bulk structure. So that'll happen for many of you if you get into developing complex combinatorials and things like that. And in that case, what I'm showing over here on the right is a frequency sweep where I told the system, hey, start at like 0.4 megahertz and go all the way up to 3. And every time you step forward, report back to me what the displacement of this fiber tip was. So now I'm actually able to optimize by just looking at this output what my best frequency output would be. And here you can see that it happens at about 0.7, 0.8 megahertz. And I did this little multi-day to figure out if I could reassemble this and see if the signal was still stable. So I hope everyone appreciates frequency sweeping, and Kim mentioned it's used for a ton of other things. Okay. So another thing, Kim.
What is that burst button for? I mean, it's interesting because in ultrasound imaging, burst just means a long pulse. And sometimes people use it to mean other things when we're trying to move away from that. What does it mean here in this context?
It does actually mean, and maybe we'll come to a standstill on this, but on this machine, a burst is literally to run a certain number of cycles at a certain frequency, and then to define the intercycle, or sorry, the interpulse interval. So I think it actually just means exactly what you're describing. And you can program a PRF, or pulse repetition frequency, using the function generator directly.
No, actually, so in ultrasound imaging, a burst is a single long cycle, a long pulse. It's not a repetition of pulses, but people have used the term where you repeat a number of pulses using the term burst. But now I can see why they used it because of this.
Yeah, well, you can program this to have just n of one burst, in which case then it might look like an ultrasound imaging system. But because you can do more, then it becomes more of a flexible kind of outcome. Do people ever use these types of, do people use function generators in imaging research? Maybe. Okay, maybe from that. So Kim, you were asking also, oh, I guess you were asking about burst. So I'm glad we've described that there. So what about these output channels? So Kim, you can correct me if I'm wrong, but I think the origin of this type of output, and these are called BNC connectors. So here you can see, and we'll just zoom in to the cable that connects to these, but there's a female BNC connector where it has this input sector, and then the male BNC that has the actual input itself. And you can see these sort of little locking mechanisms, and we'll show you during the class how to connect these, but you essentially slide these rings together and lock them in. And this cable is just a common interface to connect equipment. I think these were really developed around radio frequency labs and things like that. But people use them in ultrasound very commonly to essentially get a coax, positive and negative. So here I think it's the positive is the inside and the negative sort of the outer ring. And you can connect various tools. And these are very common to function generators and other systems. It's also worth noting, and we're going to get to this in a bit, that the source of your center frequency or your waveforms is usually operating with a 50 ohms electrical impedance, and that these cables where you might connect devices are also at 50 ohms. And you always want to check the electrical impedance of your system, because you're going to get things, something called an electrical impedance mismatch. It's a lot like our acoustic impedance mismatch, and I think that's coming up in a minute. Kim, we already talked about modulating signals. Should we talk about it again really briefly?
Yeah, sure.
Okay. So you can have your center frequency, which we've already shown you here might look like just a regular old sine wave, but you can also multiply that with a different, slower, or different shaped waveform. And this allows you to sort of change the structure of this underlying oscillation. And to do this with a function generator, you would hit this mod button and you'd look through a bunch of settings, and it'll ask you, do you want to do amplitude modulation? Do you want to do frequency modulation? And you can use an external input modulation signal. So on the back of this system, you can't see this, there's an AM input. So that's an amplitude modulation input. And by hitting this button and selecting AM, the machine itself will now modify the signal and multiply them together. And I'll show you what that looks like. So I do this commonly. Kim's lab also does it, and she'll actually tell you in a moment why. But here's where we're running one function generator with a carrier frequency sine wave, sorry, shown over here. And then another one, we have an arbitrary waveform that we told you about, where it's just this literal function that we've programmed into it to have this slow rise and then the slow offset. And when you multiply these two together, that your amplitude modulation function will do, you'll get this weird looking, smoothed out sort of square wave. And here you can see me measuring with an oscilloscope my pre-modified and my modulated waveform. And Kim, I know we're using this for our animal models, but does this kind of effect happen in humans as well?
Yeah, as a matter of fact, there have been a couple of studies on that. There was one that came out of Oxford where they were applying ultrasound to the head and they found that the humans could hear it. And then they were able to sort of mitigate what they could hear by adding like a sound masking. So that's something that's ongoing. And there was another study a couple of weeks ago at the Fun Conference where Brad Treby and his group at University College London also did the same thing. And what they did was they smoothed the waveform like we're doing, and similar to what your plot is at the lower plot there. And they were asking their subjects whether with the smooth waveform, they could still hear it. And it turned out that like half of them still could and half of them couldn't. And that's really interesting to me. It'd be really interesting to find out, like, is that because of their skull characteristics? So I don't really know the answer to that. They didn't have the imaging, but definitely they can still, yeah, it's still an issue that needs to be sort of worked out in the field.
Cool. Yeah, I remember one of the patients heard like a screeching animal, and then the other patient couldn't hear it. So there's sort of a lot to be discovered about why or why not people can hear ultrasound. It's pretty exciting. Yeah. Okay, let's take a quick peek at the system. Did we get through everything? Oh, so let me just go really briefly into a sink and an output. So the sort of sync BNC connector here just allows you to send out individual triggers. So you might send out something like a square pulse to tell other systems when your function generator starts its output. And the output BNC connector itself is very literally just carrying the function that you've told it. And I think we sort of skipped past this, but any different function you have here has a number of different properties. Kim mentioned one is the fundamental or carrier frequency. Here it's 10 megahertz, you can see. It also will ask you for the amplitude. So that's how much voltage, you know, it could be peak to peak or just from the sort of zero state to the peak. How much voltage are you kicking out? And these machines, I think, usually only kick out to like 1 or 2 volts peak to peak. Maybe 5, like 5 volts might be actually, depends on the system. And then you can also apply an offset so that your sort of center of your oscillation is actually plus or minus some voltage. Mm-hmm. Okay, and I think we're going to show everyone this in our hands-on lecture, so you'll get some chance to experience this yourself. Okay, so let's actually we'll drop further down the network here. So our function generators are over here. They're kicking out a certain signal, and we're dumping this into a power amplifier. Okay, so Kim, why on earth are we trying to power it up if it's, you know, coming out at 1 volt?
Well, that's a really small signal, and what we need is more power. And so we're going to have to amplify the signal.
Yeah, and really low, you know, really low displacement and low pressure might be okay for really like low sensitivity imaging, but for neuromodulation, we really want to get a lot of pressure into the system, comparatively speaking. So often we need these pretty hefty power amplifiers. And there are a lot, if you know your system very well, you can custom design very small, very efficient amplifiers. But when you're doing research, you don't always know what frequency you're going to operate at. You don't always know, you know, impedances and things like that. So you can buy these very standard RF radio frequency power amplifiers. And something that you want to look for when you're buying these amplifiers is, well, what's the bandwidth? Is the operating frequency that I want to do within this bandwidth. And you want to get that as tight around your range as possible. The larger the RF bandwidth you get for one of these amplifiers, it can like double the triple the price very quickly. And of course, your range, you know, should capture your frequency. You can also look at the rated power limit. So Kim and I were just talking about somebody was asking for an amplifier that might need like 500 watts. So this amplifier in particular is only 100 watts. So it wouldn't maybe be sufficient for their application. So you want to know what power you need. And you also want to know the gain. So this will be for voltage or for power, but you can get sort of like, this one's a 53 dB amplifier. So you can take your voltage input and ask about how much that's going up. Okay, and I will jump to the last little bit of our sort of basic setup here. And this is not an essential requirement, but very often you'll want something called a matching network. So as the name implies, we're trying to match something. And just like an ultrasound acoustic wave traveling through tissue, electrical alternating currents can travel through materials that have different electrical impedance. So a willingness for that sort of AC voltage to travel across as a wave. Okay, so just like acoustics, let's imagine that our piezoelectric does not have the same electrical impedance as our source, which in this case is our amplifier. And as I mentioned before, your cable, your function generator, and your amplifier are probably all matched to each other. They're probably all 50 ohms. You can buy different electrical impedance matched systems, but it's typically 50 ohms. But your piezo might not be 50 ohms. And in that case, much like our acoustic wave, you'll start to get reflections at this interface where your wave will bounce off, your two different acoustic impedances and travel backwards. So why do you think that's a problem, Kim?
Yeah, you're just going to lose power input.
Yeah, so your system is now less efficient than it could be.
Mm-hmm.
You have to use higher voltages and higher powers to get the output onto your system. So in that case, you would want to go ahead and design a matching network. If you don't have a matching network and you're getting totally enough power, then maybe you don't need it. And maybe that's something you can forego. But if you do need it, we're not going to tell you exactly how to get there, but we'll tell you the basics. The basic idea here is that you have some sort of a source and you have your output of that source. So in our case here, it's going to be our amplifier. That's going to have an output impedance, and your load, which is again your piezoelectric crystal, is going to have its own impedance. And if you want to maximize power, your load impedance should be equal to your internal or output impedance. And as soon as you start to lose that balance between the two, you're starting to lose efficiency. So then that requires more battery or power usage. And also it may cause more heating in your wire because you're getting sort of these standing waves or bouncing back and reflecting power into your wire. Okay, so I already told you, we're not going to teach you how to build this system, but we can already, say up front, there are lots of instructables and ways that you can change the cabling or to create intermittent circuits that have inductors and capacitors that allow you to artificially or actually match your load impedance to your output impedance. And maybe we can talk a little bit more in the class about that. Okay, so that covers our entire circuit here, and I'll just bounce back to it. But again, we have your CPU, which you may or may not have, that controls your function generators, generating your signals. You can modulate them or not. Of course, you want to amplify them to get your desired power or pressure outputs in the system. And this matching network, which you may or may not need to minimize the reflection between these two systems. And now we'll jump into our next lecture.
Okay, so let's wrap up this lecture. We talked about piezoelectric crystals with some of the important information about them, resonant frequency, backing layers, matching layers. We talked about transducer spec sheets. And then lastly, Keith gave us a bit of information about system hardware, including function generators and power amplifiers and matching layers. Okay, so we're going to call it quits here. And the next lecture will be on transducers, and we'll get into single element and then arrays. And in addition, I want to draw your attention to there being some supplementary material in addition that will on sort of beamforming. Okay, that's it.